This is lecture 9.5, which is the theory of why salts can create pHs that are not neutral. So you should have already started your learning targets and have a basis of the cations and anions that are not neutral and why they're not neutral perhaps. I'm going to spend most of the lecture focusing on the why rather than the what. So you will definitely want to make sure that you memorize the what and that you understand the why. So go ahead and stop the video if you need to still do learning targets, and then come back as you're ready to start adding to what you have. Okay, so the first thing that you have to recognize is that when we put a salt in water, the first thing it's going to do is dissolve. So if it's an insoluble salt, then for the most part, we're not worried about whether or not it creates a pH because it's insoluble. But if it's a soluble salt, you have a decision to make about both the cation and the anion and their effect on the pH of the solution. So typically, for the most part, your rule of thumb is that you're going to decide if the hydroxide ion, if the cation can kind of reach in, picture it as a Bronsted-Lowry, well, not really Bronsted-Lowry, but reach in as a reaction to pull out the OH minus. And so there's several things like the cation of a weak base or the small highly charged metal cations. This doesn't really work for, but you're trying to decide basically if it's going to pull out that OH and leave behind H pluses. As another rule of thumb, you're going to be looking for whether the anion can actually pull the H plus out of the water. So these are the things that you're kind of on the lookout for theory-wise. And then you have to start to recognize that if the possible product of the reaction, when that is attached to the portion of the water, is a strong base or a strong acid, then it's going to be 100% soluble and that reaction will not occur. So you have to kind of focus on, will a reaction occur between the cation and the water or the anion and the water? And if it will occur, then you have a change in pH from neutral. And if it won't occur, then water will pretty much remain water, and the hydrogen or the hydronium ion and the hydroxide ion will be formed only in equal proportions based on the Kw. So this sounds really complicated, and it's not as bad, I don't think, as your book makes it sound or as I just made it sound. So let's kind of walk through this quickly to give you some ideas of how this works. Your book separates it into like all these different categories of a salt that has an anion of a strong acid or a cation of a strong base. I just kind of always look at the first half of the compound as the cation, and if it's an acid or neutral, and in the second half, if it's a base or neutral, and very, very every once in a while might be an acid as well, and then kind of put the two together. So rather than memorizing all those, I think it's more to memorize the way that your book discusses it. You can kind of decide which way you like it better. So I divide cations into two categories, cations that are neutral and cations that are acidic. So you need to make sure absolutely that you know which ones are neutral. So the group 1 metal cations and the bottom of group 2 metal cations are going to not change the pH of water. So notice that these are the cations of strong bases. All right, so in other words, this would be like if it made the base, it would be NaOH or strontium hydroxide as such, and those would be the cations of the strong base, right? So this means that they cannot hang on to the hydroxide from the water. They cannot actually reach into the water molecule and pull out the hydroxide and create a reaction there. So I'm going to show you how this works just so that you can kind of picture it. If you were asked to justify why, you could write the equation as Na plus the cation plus water, and I'm going to write it as HOH so that you can picture that the sodium ion would be trying to come in here and pull out the hydroxide ion to make a reaction. And then that's going to form sodium hydroxide if that works, and leave behind H plus ions, which means that it would definitely be acidic if this could occur. But notice that sodium hydroxide is a soluble salt, 100% soluble salt, is a strong base. and it will 100% ionize. And so at this point then, this remains Na plus and OH minus and is not the NaOH compound. And as soon as that OH minus and those H pluses are floating in water together, they're more likely to form water. And notice that now what I started with equals what I ended with, and there was no reaction. So this is the reason that having sodium ions or potassium ions or strontium ions, etc., in water is not going to affect the pH. The water will remain neutral because mostly you still have water molecules, and if you don't, they're equally forming hydrogen ions and hydroxide ions. Okay. The anions you can categorize as mostly neutral or basic, although there are a few that would be acidic. And so we want to make sure that you're strong with the ones that are anions that are neutral. So again, these are the anions of strong acids. So this would be like the anion of the strong acid HCl, or the anion of the strong acid HBr, or the anion of the strong acid HNO3. So there we're talking about all of those anions. Okay, so reach in, picture that the anion would be reaching into the water and attempting to pull off, it's negative, so it's going to attempt to pull off the hydrogen ion, and it would attempt to form HNO3, and it would leave behind hydroxides. So if it's able to do this, it's definitely going to create basic solutions. However, HNO3, just like up here where sodium hydroxide was a strong base, HNO3 is a strong acid. It 100% ionizes and turns into hydrogen ions and nitrate ions. And again, those H pluses and OH minuses are more likely to be water, leaving us with what we started with and no reaction. So again, these are going to create no change in pH. The only pH creator based on what's happening is our water, which is going to ionize equally into hydrogen and hydroxide. So the pH should remain neutral. So those are the neutral ions. Everybody else has an effect. And so you need to kind of keep in mind that cations are typically going to be acidic if they're not neutral. And there are two basic categories of these. So actually there may be another category, and so I can kind of show you that, but the two main categories of these would be the cations of what we call weak bases that are amines. All right. So notice that these have that NH 4 plus or the NH3 with this extra carbon chain on the front. It could be a bunch of carbons with an NH3 plus, but notice that these have this extra positive ion, and you have to start recognizing that those ions are indeed weak acids. Okay, so really when we say that the cation of a weak base, we're really saying that they are the conjugate of a weak base. Okay, so they are the conjugate acid of a weak base, and that makes them acidic, right? So these will be Bronsted-Lowry acids in water, and if I put methylamine in water, then I'm going to have CH3NH3 plus water, and this is a Bronsted-Lowry acid-base reaction. It's going to transfer a hydrogen to the water. It's going to make the hydronium ion, and then the this is methylammonium, and now it's going to make methylamine, which would be CH3NH2 neutral, right? And so because of this, and this fact that this reaction will form something that is a weak base and will not ionize 100%, now we have a reaction, and so now we see that we have H3O pluses floating around in solution, which will make the pH acidic. And if I needed to figure out the pH of this, I would have to know the initial concentration here, and I would have to know Ka for CH3 and H3+, which I might have to find from the Kb of CH3 and H2 neutral, if that was what I was given, but I would be able to then solve for X and notice that X is hydronium and find the pH. Okay. The next thing I want to look at then is the other acidic cations, and these are ones that create complex ions, and so you haven't seen this before, but they are usually small, highly charged metal cations. So this is mostly your period 4 transition metals because they're relatively small, We don't see it really in the transition metals that are larger than that. And then magnesium and aluminum, because magnesium is not the cation of a strong base. Remember that magnesium hydroxide is considered to be relatively insoluble, and aluminum is also like pretty small. It's actually the smallest of all those metal cations in that category, that they're not group 1. So these guys are likely to do what we call forming complex ions when you put them in water. You will not need to know how many waters would attach to make this complex ion, but notice that this is like a great big huge polyatomic ion where actually it's aluminum and a bunch of waters together. Since water is neutral, the charge is the same as it would be on the charge of the aluminum cation. Okay, so picture that if I put this in water, this is kind of a fun reaction. If I put this in water, what it does is act as a Bronsted-Lowry acid, which means that the only hydrogen it can give away comes from the water and forms hydronium. And that leaves behind this really complicated aluminum with now 5 water, because we got rid of one, and an OH, because we got rid of a hydrogen. Okay, so one of the 6 waters turned into hydrogen and hydroxide. The hydrogen transferred to the water to make hydronium, and the hydroxide ion is left behind. And now, because it's missing a positive charge, it now has a total charge of 2+. So these complex ions used to be part of the curriculum in AP Chem, and they've kind of removed it other than the idea that they exist like this. And so this would be hexaaqua aluminum 3, or hexaaqua aluminum. We don't really need the Roman numeral 3 because we know aluminum's charge. But this would be occurring maybe with iron or with magnesium, or perhaps with nickel or copper, all those small, highly charged metal cations. And so we have to always keep an eye out for what's happening there to see whether or not this is going to be the case. You won't have to know how many water. They all have different number of water. But you should be able, if you know the complex ion, to see that one of the water will turn into hydrogen and hydroxide, leaving you with fewer water, and then allowing it to be a Bronsted-Lowry acid. Okay, technically, this could do this again, maybe 5 more times. It won't do it again that many times. Eventually, it will become a base and be more likely to accept a hydrogen. But this could be a polyprotic Bronsted-Lowry acid. So those are kind of cool. The one that I didn't put in my PowerPoint here is the idea that maybe I have silver, or I have platinum. Those are really not very reactive as metals, and they're not likely to form those ions in water, which is good because we use like a lot of those things for our for pipes, etc. Actually, I don't think copper does this because we wouldn't want it to do that with water. But what you're looking for is every once in a while you might see a metal that if you put it in water, it could pull off the hydroxide and leave you behind with hydrogen ions, which would also make it acidic. That's really rare, so most books don't talk about it. All right, finally, we need to talk about some anions. And anions are typically either neutral or basic. So the anions that are basic are those that are the anions or the conjugate, I can't spell today, conjugate bases of weak acids. And so you should already be recognizing these. Again, this is the Bronsted-Lowry base, right? That's the anion. So for example, if I have SO4 2-, it can react with water to accept a hydrogen, which is what bases do for Bronsted-Lowry, and become HSO4-, SO4 2- can react with water to give you HSO4- and leaving behind the hydroxide ion. And since HSO4- is a weak acid, the hydroxide remains in solution, and now it's basic. Again, if you wanted to find the pH, you would need to know the initial concentration of sulfate, and you would need to know the Kb of the sulfate ion, which you might have to find from the Ka of the hydrogen sulfate or bisulfate ion. So you could do this, and you could calculate it by solving for X down here, and then X would be the OH-, and you would need to find the POH and the pH. All right. Finally, let's add a little bit more to this. I hinted at this, that there are anions that could be acidic. And so your anions that could be acidic are going to come from your amphiprotic anions. They're not all acidic. Many of them are still basic. You should probably know that HSO4 minus is acidic, that H2PO4 minus is acidic, and that HPO42 minus is basic, and that bicarbonate, HCO3 minus, is basic. You should probably know these. These are ones that you encounter a lot. So even without knowing the Kas and the Kbs, you should probably know that. But if you're given Ka of something, you can figure out whether it's acidic or basic based on whether Ka or Kb for that same exact thing is bigger. So remember, you can find Ka and Kb of conjugates using Kw, but you can't find it for the same thing using Kw. So let's do an example so that you can kind of see what's happening here. The Ka, if I'm trying to figure out if this HC2O4 1- hydrogen oxalate is acidic or basic, I need to know its Ka and I need to know its Kb. So when I look it up, I see that I can find its Ka as 5.4 times 10 to the negative fifth. So this I found on a table, all right? But the problem is that I can't find the Kb of this on the table. So when I looked at the table, I was given Ka of the conjugate. This is really hard because you have to really make sure that you're not trying to say Kb of HC2O4 1- equals the 1 times 10 to the negative 14th of the Ka of that same ion. Remember, Ka and Kb multiply together only for conjugates. So if I have to find a Kb, I have to find it from the acid that would form this base. Okay, so when I did that, I would say Ka of H2C2O4 divided by Kw would give me Kb of HC2O4 1-. All right, so this is a little bit more complicated, but that means that the Kb equals 1 times 10 to the negative 14th divided by 5.6 times 10 to the negative second, which comes out to 1.8 times 10 to the negative 13th. So right now you can see right away that the Ka of this ion is 5.4 times 10 to the negative fifth. And the Kb of this same ion is 1.8 times 10 to the negative 13th. And since its Ka is greater than its Kb, this ion is an acid. It's more likely that when you put it in water, it will transfer the hydrogen to water than if you put it in water, it will accept the hydrogen from water. So those are what the values of that mean. And when it transfers that hydrogen to water, it's going to form the hydronium ion. Okay, so at this point we would have an acidic pH based from that ion. That's kind of confusing, so we need to rewatch that section. Finally, what I do always is go, okay, I have a salt, so maybe I have sodium hydrogen sulfate, and I can look at this salt and say, well, this is neutral because it's the cation of a strong base, and this is acidic because it's amphiprotic, but it happens to be one of the amphiprotic ones that's acidic. So overall, this salt will give me an acidic pH because neutral has no effect and the anion is acidic, right? I could also say that maybe I have ammonium chloride, and I could say that the chloride is neutral because it's the the anion of a strong acid, and the ammonium is a Bronsted-Lowry acid, so it's acidic, and in this case, again, this would be an acidic solution. But sometimes we see that we don't have the cation or the anion of a strong base included at all, which means that we need to put the effect together, and it's a little bit harder. You have to find the Ka of the cation and the Kb of the anion to decide which one is more likely to be to produce hydrogen ions or hydronium ions, or hydroxide ions, and which one's better at it. Because they will both be doing that, you have to decide which one's going to produce more. Okay, so whichever Ka of the cation or Kb of the anion is larger kind of wins. It's better at producing hydronium or hydroxide. So for this one, I chose ammonium chlorite, and ammonium has a Ka. So neither one of these is the cation or the anion of a strong acid or a base. So ammonium has a Ka of 5.6 times 10 to the negative 10th, and it would be acidic, all right, because it's a Bronsted Lowry acid. It's one of my amines that has already gained a hydrogen. And chlorite could be the anion of a weak acid, right? Its conjugate acid would be HClO2, which is a weak acid. So it should be a base. And so now I need to decide which one's better at this. Okay, so I compare the Ka and the Kb, and I can see here from these two values that Ka is greater than Kb, because it's 10 to the negative 10th and Kb is 10 to the negative 13th, which means that ammonium is a better acid than chlorite is a base. All right, so ammonium will be producing lots more hydronium ions than that chlorite will be producing hydroxide ions. So overall, this will be slightly acidic. Okay, and if you had to calculate the difference, you would need to use your ice chart for ammonium in water and form the hydronium and the NH3. And you would need to find the X, which is the hydronium. And then you would have to do the same thing with the chlorite in water and treat it as a base. So it's going to form HClO2 when it accepts the hydrogen, leaving behind hydroxides, and you would have to find your hydroxide concentration at equilibrium from your ice chart. And once you do that, then you can take the difference, because remember that the hydronium and the hydroxide would actually probably react together to form water in some capacity, all right? And so the difference in hydronium concentration and hydroxide concentration, and whoever's excess, then you can take the negative log to find the pH. This is unusual that they might ask you to do this, but I need you to see the conceptual idea behind it, okay? So we'll practice this in class. You'll do some actual calculations of pH, you'll do some decisions, and I'll pull out some solutions so that you can find the pH of them and see that it is really true that they are the pH that you're expecting, and we'll go from there. So come ready to practice.